Okay, so the point of this video is to prove what was asserted in the main theorem in the previous video. In other words, that the Laplace transform of f convolved with g is equal to the Laplace transform of f times the Laplace transform of g. And to do this, all we're going to do is just compute the left-hand side and show that it is equal to the right-hand side. So there's going to be a string of equalities, and what's going to happen is that at the end of that, we're going to get f of s times g of s. Okay, now this involves a multi-variable change of variables in integration, something that you learned in Calc 3. If you haven't had Calc 3 yet, I don't know if you're going to be able to follow all of this, but that's fine because I'm not going to ask questions about this on the test or anything like that. But eventually you'll get to that in Calc 3, and then you can come back and watch this video. Okay, so I'm going to begin just by what is the definition of the Laplace transform of the function. Well, the left-hand side is the integral t equals 0 to positive infinity f convolved with g of t e to the minus st dt. All this is the definition of the Laplace transform of any function. Okay, so when we want the Laplace transform of f star g, this is just the formula. Okay, this has nothing to do with convolution yet. It's just the formula for Laplace transforms. Okay, now I'm going to plug in the definition of f star g. So I'll have an integral t equals 0 to positive infinity, and on the inside I'm going to have an integral tau goes from 0 to t f of t minus tau g of tau d tau, and then on the outside I still have e to the minus st dt. So now I'm just going to kind of write this without the brackets. This is going to be the integral from t equals 0 to positive infinity, the integral tau equals 0 to t f of t minus tau g of tau e to the minus st, and then d tau dt. Now, it might not seem obvious, or you might not understand why, but observe that what I want to do is I want to swap the order of integration. So instead of integrating with tau on the inside and t on the outside, I want to integrate with t on the inside and tau on the outside. And the reason is because if I do that, then on the inside I'll have e to the minus st dt, and that kind of looks more like the integral in the definition of Laplace transforms. Okay, but remember, when you switch the variables in a two-dimensional integral, you have to be a little bit careful. So first I want to sketch the region of integration. So when I do that, I can just do something along these lines. So I'm going to call the horizontal axis the tau axis, and the vertical axis the t-axis, and I'm integrating from tau equals 0 to t. So for every fixed value of t, tau is going to go from 0 to t. So if I call this line here, if this is the t is equal to tau line, I see that for every fixed value of t, the inside integral goes from tau to t, and then t goes from 0 to positive infinity. Okay, so I'm integrating over this infinite region here, where it's above the t equals tau line, and tau goes to infinity, and t goes to infinity as well. So when I change the order of integration, so I'm just going to write the integrals here. I'll rewrite it again, but I want to have t on the inside, and I want to have tau on the outside. Now I know tau is going to go from 0 to positive infinity. You can just tell it from this region up here. Tau goes, the smallest value that tau is 0, and the biggest is going to be infinity, because this, again, this is an infinite region above the t equals tau line. So I know tau goes from 0 to positive infinity. Now what about t? T, for every fixed value of tau, will go from tau up to infinity. So now for every fixed value of for every fixed value of tau, t goes from tau to infinity. So this is going to be tau to positive infinity. So if I want to switch the order of integration, this is how I switch the integrals. Okay, and this is equal to the integral tau equals 0 to positive infinity t equals tau to positive infinity f of t minus tau g of tau e to the minus st dt d tau. And all I've done to go from this integral to this integral is just this change of variables. And if you are a little rusty, you can review that in Calc 3, or from Calc 3. And so this is equal to the integral tau equals 0 to positive infinity g of tau. And now the inner integral, I'm going to put the brackets back, it will make sense in a moment. This is going to be the integral t equals tau to positive infinity f of t minus tau e to the minus st dt d tau. Okay, now this inner integral looks kind of like the Laplace transform for f. The only problem is that the integral starts at tau instead of 0, and I'm integrating f of t minus tau instead of just f of t. So I'm going to do one thing that fixes both of those problems, and that is u sub. I'm going to say that u is equal to t minus tau. If u is equal to t minus tau, this means that du is equal to dt. And also if u is equal to t minus tau, this means that t is equal to u plus tau. And now I'm just going to rewrite the integral, the inside integral, using this change of variables. The outer integral is going to stay the same. And so this is going to be the integral tau equals 0 to positive infinity g of tau. Now this is going to be where the inside integral goes, and then I'll go ahead and write d tau. So the inner integral, when I do my change of variables, the f of t minus tau becomes f of u. The e to the minus st becomes e to the minus s u plus tau. Since t is equal to u plus tau, the dt becomes du. And for the limits, well, u is equal to t minus tau. And if the lower limit is t is equal to tau, this means I'm going to have the limits going from u is equal to 0 to positive infinity. Now let's make this following observation. This exponential, e to the minus s times u plus tau, can be written in the following way. It is equal to e to the minus su e to the minus s tau. Now as far as u is concerned, e to the minus s tau is a constant. So I can pull this constant here. Okay, so now look at what is happening. The integral inside the brackets there, that is exactly the Laplace transform of f. So this is the integral tau equals 0 to positive infinity g of tau e to the minus s tau times the Laplace transform of f evaluated at s d tau. Okay, well, as far as tau is concerned, s is a constant. And so this is the integral, or this is f of s times the integral tau equals 0 to positive infinity g of tau e to the minus s tau d tau. Okay, but what is this integral? This integral right here is nothing more than the Laplace transform of g. And so this is equal to f of s times g of s. And that's exactly what we wanted. So we have this string of equalities. We began simply by computing the Laplace transform of the convolution, then inserting what the definition of the convolution was. Then we did some change of variables and some rearranging of the integrals. And at the end of it, we showed that this is equal to f of s times g of s, which is exactly what we claimed it to be equal to.